All right. So let's remind you about what's the first derivative test and second derivative test. Okay. So this is first derivative test. Okay, so this tells you about what's a local min and local max, the criteria for local min, local max. So basically you have, say, sign chart. Chart. See. Okay. And this is positive to the left of, so this is derivative, sign chart for prime, for first derivative, and then negative to the right. Okay. So, and here the second here is the other way around. So negative, this is positive. And this one, same sign. And the conclusion is that this is the kind of the identifications. When you have something like this, then you have local min here. Sorry, local max. In this case, you have decreasing, increasing, you have local max. Sorry, local min. And this both neither min nor max. Oh, sorry. Hello.
Yeah, hello, sir.
Sorry, get disconnected. Let me share screen again. All right, so this is the first derivative test. So basically tells you about max, local min or max based on change of signs for the first derivative. Okay. Now, second derivative tells you about, all right, this local min or max. So it can be something that looks like that one or this one. Okay, so this is local max. And local min can be, in this case, this is a stationary. This one is singular. Okay. See the difference? All right. And we have also what we call second derivative test. Actually, this is the thing that you used it in when you're in high school, second derivative test. So you compute the first derivative, find the stationary point, and then again, find the second derivative. So the assumption is that first and second derivative exists. Okay. And so it has more restrictions than first derivative test. Okay. And this tells you that when second derivative is negative, meaning this is this is stationary. Okay, so that's not singular. All right, when you have stationary point, when you have this is negative, concave down. Here one concave down, so that means like this. Then it is max, local max. And this is a concave up. And you have some, it looks like this one. Let's give you local min. Okay, so the second derivative test is more restrictive than the first derivative test. And then it does not include the case for singular point like this one. No. Second derivative test is more restrictive. Okay? It's more restrictive. Uh, and also it is does not cover either point. Okay? So in this case, second derivative test is less useful than the first derivative test. Okay, so we just keep using this first derivative test. Okay, we'll find this the theorem with second derivative test next semester for two variables or more. Okay, but at least for graph sketching, we only need the first derivative test. Okay, so that's one thing that you learn from high school, but we won't use it here. Okay, so let's get on to some word problems. On to word problems. Let's see. Practical problems, 3-4. Let's take some problems from the all right, so let's pick one problem here. Okay. Uh, all right, so let's this problem 12. Right, so this is the problem that you have a 180 feet of fence. So this is the fence. And wants the pen to adjoin the whole side of the 100-foot barn. This is for barn. This, this one is 100. Okay. Now, how would we, what should be the dimension for the maximum area? Maximum area of the pen. Okay. So burn joining here. Okay. So can we model this one? And what the maximum? Okay, so we know here. All right, so that's what is that 180 feet of the fence? Where's the fence is? The fence is this part. So just X and then Y here. Okay. And this is another X. And this part, little part here. That is this is Y minus 100. Okay. So that's 180 is the length of the fence is just X plus Y plus X plus this 8. Okay. And X should be the range. There we go. And then what we need? We need to maximize area. And it's just X plus Y. Okay. So, but this is two variables. So we need to reduce to one variable. So just use X or Y. But how to use this one? Find out the other variables using the one we fixed here. Okay. All right. So let's do this one. Okay. For the length of a fence, we have X, uh, 2X plus 2Y minus 100 plus 180. Okay. So X between us. Okay. This is what we call a constraint. Okay. So the restriction. So conditions. And then the objective is to uh, maximize okay, so reduce it to one variable. So X times, let's see, Y is 180 plus 100, so 200. So from here, Y equals 280 minus 2X over 2. Okay, so we have here Okay, so that's easy. This is a, oh yeah, that's it. This is what we call objective functions. AX. Okay, so maximize EX, right? So once you get the formulations, then that would be easy to find, because what we need here to just to find first derivative, but that's easy because that's a, say this is 1 times, so let's see, 140x, 140 minus x squared, so minus 2x. And let's give you uh, just stationary. X equals 70, right? No singular. But the thing here, if you have endpoints, because of these restrictions. Oh, sorry. X, 70 is just outside this one here. Let's see. Made mistake or not? X, Y. We make a mistake. X to Y minus 100, 180. 80, 3 minus X. All right. Okay, sign for this would be negative. All right. Okay. All right. So this is negative, negative, positive. But what we observe is only here. It's going down. Okay, so what's the conclusions? When x is maximum, we make some mistake here. So the maximum would be at 0, but at 0, you don't have an area at all. Okay. Where do I make mistake here? Anyone see the mistake? The max would be at 0, but at 0, you don't have the area. Uh, uh, 17. Okay, okay. Let's see. This cannot be true. This is incorrect. Yeah. Let's see. Wrong sign. So the sign for this would be, oh, that's easy. All right. This is a quadratic. A quadratic is supposedly to be a parabola, right? So opens up or opens down because this is negative minus x squared. So you have parabola opens down. So it looks like this. Okay. So the vertex of the parabola gives you the maximum. Okay. So here's the 0. Here's 140. So the vertex should be at x equals 70. Let's give you, here's the vertex. Because it's going up, then it's increasing here. Okay. So the sign should be, let's check the sign here. See? So this should be negative. This is positive. There. So the picture should be, looks like this one. Okay. But because we just restrict between 0 to 40, then we know that the 40 should be the maximum. Okay. So in here, outside the range, outside this area. So no singular point. Okay. So that's why you just need to find the critical points only at endpoints. Okay. Since the function is increasing, then the max should be located at right endpoint, which is x equals 40. So let's give you the maximum. Okay. Oh, the question is the maximum area. The dimension for the maximum area. Okay, the dimension. So dimension for maximum area is x equals 40 and y equals, let's see, y is, let's see, what is y? So 140 minus Okay. All right. Questions. Okay, so that's you see what's important here is the sign for derivative. Once you mess up the sign, then you may mess up the whole thing. Be careful with sign. All right, questions?
No, sir. Thank you.
All right, all right. If not, then let's problems. All right, so this one, problem 19. Okay, here's the situations. Small islands 2 miles from the nearest point P on the straight shoreline of large lake. Okay. If a woman on the island can row a boat 3 miles an hour, that's the speed, and walk 4 miles an hour, where should be the boat be landed in order to arrive at the town 10 miles on the shore? All right, so this is the situations. Island, this is the shoreline. Okay, this is the point P. Okay, so from island to the point P, one has to row a boat. One. And then this is the boat is 3 miles an hour. Okay, and can walk 4 miles an hour from here on land. All right, so there's a town here. And miles. This is 3 miles. Okay. So the question here is that where that person should be land here or somewhere here to minimize. Let's see, this is the on land is 4 miles. In order to arrive. So, okay. So the thing here is that find a point, some point here, so that okay. There, that's the question. So the problem should looks like this one here. So this is 3. This is, the whole thing is 10. So for example, land here, say this is x, 10 minus x. Okay. So then this distance here should be, what should be the distance here? Well, that is the square root of 9 plus x squared. So that's the distance. And you have to take that 3. Okay. And then this distance is 10 minus x. And with speed 4. Okay. All right. So this is the water distance. This is the land distance. Okay. So this is the speed of the boat, 3 here. And this is speed on land, 4. Okay. So we need to find least time. So this is the total time. Min of total time. Okay. So the total time is this distance, water distance, divided by the speed. Okay, so that's 1/3 square root is x squared. And this is 5/4. So okay. So x is between, you better restrict x. This is x. So x is non-negative, but it is must be less than 10. Okay, so this is the objective function. This is the restriction here, the constraint. Objective. All right. When you get these formulations, it's basically about half of the work that you need to do actually. Okay. So next is the minimize the total time.
So can I have a question?
Yes, sure.
Can I ask? Well, for the velocity, why is it turned into 1/3 and 1/4?
Because this divides, right? You divide the distance by speed.
Oh, okay.
Of course, you can write this as a division, but that's the same thing. Okay, so this is a p of x. So minimize total time, so you need this derivative. So you need to find the critical point. Okay, so let's take, this is power 1/2, right? So this 1/6 plus x squared power negative 1/2 times derivative of x squared is 2x. Okay, here's that's the same. It's easy because this just minus. Okay, let's simplify. Just 1/3 x. Okay. So let's yeah, take it equals 0. Okay. So if you solve this one, what you get actually? Let's see. This is positive thing, so you you won't get any no critical, no singular point. You see why I said it's no singular point? So there's no way you can have this denominator equals 0. Right? This is always positive. So there's no singular point. So the only thing is that the what you call the critical point, the stationary should be that's okay. So you solve this one. Uh, basically, you just square it, or you can solve that using x. The problem itself set this one, meaning use calculator. Okay, so let's go to the our maple. Let's say let's solve. Uh, 3 times square root of, let's see, 9 plus x squared. Where is that thing? Power. Power. Yeah. Equals x. Solve for x. Ah, that's the x. Okay. 9, 7. All right. Okay. So you can figure out what the number should be around that one kind of point. Okay. I can calculate it. right, and then check the sign. X between, and this number is 970. Pick up calculator. What should be the number? What should be the number there?
I'm sorry, sir. Number for where?
Here, 97 times square root of 7.
3.4, sir.
3.4. Right.
Yes, 3.4.
Okay, so that's here. Just plug in here. Well, say plug in 4. If you plug in 4, you get 3, 9 plus 16. Okay. You get 3, 4. This is 5. This is 3, 16, 15. This is 4 over 16, right? Okay, so this is still positive. Okay. And this should be negative. If you check. So you have there. Oh, sorry. Yeah. All right, so it turns out that this is the really local min. And because that is the only local min, it should be also the absolute min. The only one. Okay. So X should be 3.4. Sorry, any questions? Yeah. So the question is about X. So 3.4 miles from that point P. Uh, all right, any questions?
No, sir.
All right, if not, then I will start the tutorial sessions later just to finish the material. Just one more topics, that's the mean value theorem, and then let you do the exercise later with the Kakemo after that, the words. All right, if not, then let's stop the share and stop the